Good morning. I'm Susan Dickerson Lange, and I am a PhD student working with Jessica Lundquist at the University of Washington. And I'm pleased this morning to share with you some of our recent work on predicting optimal forest management strategies to maximize snowpack duration. This work is motivated by projections made by Elsner and others, as well as other investigators across the Pacific Northwest and the western U.S., that under a warming climate, snowmelt is predicted to shift earlier in the year, as well as develop less of a snowpack. And so for basins in which snow is a substantial component of the hydrologic system, such as these two examples, where we have a transient rain snow system, which has both a rain and snow component, as well as a snowmelt dominant system. So you can think of this as a lot of the watersheds on the western slopes of the Cascades versus many of the watersheds on the eastern slopes of the Cascades. We're looking at a shift from historical, this black line, the spring melt peak, to earlier in the year with less overall snow as well, and less of a shift, but a shift nonetheless in snowmelt dominant basins. Now, in addition to climate affecting the timing of snowmelt and the amount of snow, we also know that forest cover has an important impact on the amount of snow that accumulates and the timing of its melt. Starting as early as the early 1900s, and this is a photo from the mid-1900s, there were a series of watershed scale experiments done in which large quantities of the watershed were cut into different sizes, so sometimes in strips and clearings like this one, and other places more of like a honeycomb pattern of different size gaps to look at increasing overall water yield. Now, the results from these were quite scattered, and there were some issues with sedimentation and other things. But in a more modern context of forest management, where forest managers are thinking about water yield, but are also thinking about habitat and timber and soil preservation and water quality, we're building on this idea, but to look at, can we quantify the impact of modern forest management strategies on the timing of snowmelt in order to adapt to some of this shift that's projected under a changing climate? So I'm going to address this from three different scales that we've been working on. We started at the plot scale, collecting observations of snow duration in the Cedar River watershed. We then took those results to try to understand them on a global scale, looking at a global synthesis of plot scale studies. And then our next step, which we have some preliminary results from, but is still quite active research, is taking that framework we've developed to look at specifically across the Pacific Northwest, can we use this framework to apply to forest management prescriptions and guidance in the Northwest. So first, the plot scale. We've been working in the Cedar River watershed, which is about 40 miles east of Seattle. It's on the western slope of the Cascades and is managed by Seattle Public Utilities for the municipal water supply. Now, Seattle Public Utilities actively manages their forests for a number of different goals and was interested in, can we quantify the snow component of some of these forest management actions? And so we deployed a number of different types of instrumentation to quantify the difference in the amount of snow as well as the timing of that snow melt. And just from a simple perspective of time-lapse photographs, which I'm a big fan of because they give a nice visual of what's going on during the winter in some pretty remote areas, we can see that on the same day during the melt season in water year 2011, the second growth forest plot here, which is fairly densely forested, is just about melted out. There's only a few patches of snow, whereas one of our experimental gap plots, which has a gap about the size of a tree height, so about 20 meters, still has quite a lot of snow, and one of our old growth forest plots is somewhere in between. We also collected some data from various thin sites as well. Now, we've seen these results in some of the literature, but we were honestly a little surprised because conventional wisdom is that trees provide a shading effect to snow and therefore typically will extend the snowmelt season. So snow will typically last longer under trees. But we found the opposite effect here in the Maritime Mountains of the Pacific Northwest. And so we went to look at, well, what's been found around the world, and can we create a framework for where snow will last longer based on that? We synthesized 21 published studies from around the world where we could actually extract observations of snowpack duration, so how long the snow lasted, asking the very simple question of, does snow last longer in a forest or in a clearing, in more or less adjacent areas with similar characteristics of elevation and slope and aspect or the direction that the slope is facing. And we categorize them based on the triangle symbols are snow lasting longer in the forest. The circle symbol is that there's a difference of within 3 days, so basically no difference within the bounds of what we can extract from their studies. And then these square symbols, so the Cedar River watershed is right here, is the snow lasting longer in the open. So in addition to looking at those, because it's a fairly simple question, we also just started poking around at the Google Earth imagery to see if we could answer this very same question, and we can. So in the Sierra Nevada of California and in Japan, you can see that snow is lasting longer in forest gaps and clearings as opposed to actually in the forested area. Whereas in the Rocky Mountains of Canada and in northern Finland, the big clearing area is free of snow, whereas there's still snow amongst the trees. And to get at, well, how do we then predict where this effect changes, where trees suddenly go from accelerating snowmelt to delaying snowmelt? We looked at the different climatological factors of each of these sites and found a striking relationship between mean winter temperature and where snow lasts longer. So here we're looking at the difference in snow disappearance day between snow in the forest versus snow in the open. So on this side, snow lasts longer in the forest, up to about 14 days longer, whereas on this side, snow lasts longer in the open, again, about 14 days or 2 weeks longer. So we see, while there's a lot of scatter in this plot, we see that there's a relationship between places where the mean winter temperature is warmer, snow tends to last longer in the open, whereas in locations where the mean winter temperature is colder, the snow tends to last longer in the forest, with a number of sites in between where there's no difference. And this is at a very coarse scale. We're using coarse climatological data. So there's a lot of local factors we weren't able to account for here, but we did find that there's this sort of first order relationship. We use that to investigate a little further. Well, what are the bands of temperature here? So this map is colored actually by mean winter temperature, trying to take a look at this pattern. We also found a relationship between mean winter or total winter precipitation, but precipitation is related to the temperature in that our sites that tend to be warmer also tend to be the sites with more precipitation, with a more maritime or Mediterranean type climate. Now, to understand what the driving factor is in this relationship, we started looking at some case studies as well as doing some modeling. And I want to share one case study with you that nicely illustrates some of these effects. These are data, this is one snow year from 1998, data collected by Pascal Stork in Western Oregon at a site, looking at snow in terms of snow water equivalent, which is the amount of water in a snowpack, in an open site and an adjacent forested site, which is this black line. Now we know physically that the forest affects the amount of snow in a few different ways, the first being snow interception. Now, trees physically intercept snow, which leads to less snowpack in forested areas, and once that snow is intercepted, it tends to either sublimate or melt out faster. So here at the beginning of the series, we can see a steeper accumulation curve in the open area, illustrating that effect. We also know that the forest shades the snow from sunlight. And so in many locations, the snow will melt faster in an open area. And you should be able to see that in this melt curve going from the peak snow to the melting time. Now in this case, there's very little difference between these two curves, but you also have to keep in mind the time of year here. That in this site, the snow is melting in March, where solar angles are low, and in the western Pacific Northwest, there tends to be a lot of cloud cover. So it's not a huge factor at this site, but in a site, for example, in Colorado, you'd see a much steeper curve in the open site than in the forested site. Shading from wind is also an issue. For a similar reason, more wind can lead to faster melting, but is not much of a factor at this site. And then lastly, which gets to one of the main points of this temperature relationship that I've been talking about, is the influence of long-wave radiation on snowmelt. Now, long-wave radiation is also called terrestrial radiation. It's the radiation that we all emit because we're warm. So I'm probably a little warmer than you right now, so I'm emitting a little bit more. But it's the principle behind night vision goggles. You could turn off the lights and you'd be able to see all of us because we're warmer than the walls and the floor. Now, in this case, there's a photo from a site in the Sierra Nevada where the brighter color is warmer in terms of infrared wavelengths or long wavelengths. The trees are quite a lot warmer than the sky behind it. And so for snowpack under a forest, there's enhanced long-wave radiation. So it's actually getting more energy from the trees than it does in the sky, which for a site like this site in Oregon matters quite a lot for midwinter melt. So here in December and in January, we can see two specific events in which there's a melt event. In the open area, it loses a little bit of snow, but in the forested area, there's a significant drop in snow. Same thing in this January event, and this is due to that enhanced long-wave radiation effect. Now, where this matters is because of this idea that temperature, mean winter temperature, is an important predictor of where snow lasts longer. That in this site in Oregon, temperature is hovering around 0 degrees during the winter. And so this enhanced long-wave radiation effect causes midwinter melt, which has an impact then on how long the snow will last into the spring. So that enhanced long-wave radiation makes a big difference. I would call this a warm forest. For the sites in which snow lasts longer in the forest, they tend to be much colder, and so that enhanced long-wave radiation has much less of an impact on that snow. And so we're finding that somewhere around -5 degrees, in between -5 degrees and 0 degrees, there's a sort of threshold effect where that long-wave radiation makes a substantial difference in snowpack duration. So where does this matter? Our idea now is to a first order, we can predict where snow will last longer based on mean winter temperature. So applying this to the Pacific Northwest, this is just simply a map of mean winter temperature in a portion of the Pacific Northwest, ranging from less than -6 degrees to more than 4 degrees. So we're seeing a huge gradient in winter temperature, as much as we saw globally at other sites with forest-snow interactions. And so then to a first order, we think we can predict where snow will last longer based on this mean winter temperature. So just simply taking a look at that and recoloring this map based on the temperature thresholds, we can look at, well, snow might last longer in openings in this area, whereas in the dark blue, snow would last longer under a forest. And in the teal area, currently snow would last longer under a forest, but under a 2-degree warming scenario, snow that might switch and is likely then to last longer in the open. So we're trying to get at predicting more in the forest, last longer in the open or the forest, both now and in a warming climate. Now, of course, this is a very coarse model at the moment, so we're looking to validate this and refine this in a number of ways. First of all, we have some great collaborators with field sites all over the Northwest who are kindly lending us their data. These are some data from Oregon State University, from Ann Nolan's group, in which they're looking at 2 sites, one that's at a high elevation site and one at a low elevation site. And we're seeing this effect just from the elevation gradient. So at the high elevation site, snow is lasting longer in the forest versus the open, where it's a colder forest. Whereas at the lower elevation site, snow is lasting longer in the open versus the forest. So we have some sort of first validation attempts at this that we're now working through data from all of these sites. But as you can see, that there's a lot of gaps between these sites. And so one of our next initiatives next summer will be to collect citizen science data, both from surveys and from geotagged photos, because it's a fairly simple question. Does snow last longer in the forest or in the open? We had some beta testers this summer that kindly contributed some photos and surveys that were working out the bugs on that. And then lastly, our next step, of course, is to refine this to make it a much more sophisticated model and include both climate, which has been this first order effect, but also thinking about forest type and topography in terms of slope and aspect, as well as modeling the solar and long wave radiation components. The idea being ultimately to generate usable maps that look at how forest management strategies will affect snow duration now, as well as in a warming climate. From the standpoint of, for a forest like Seattle Public Utilities and the cedar, if they're already cutting gaps in terms of accelerating habitat development, where in the watershed will they want to do that based on elevation, for example, and how climate might affect that? Versus a forest on the east side, which might have very different requirements in terms of preserving forest versus introducing gaps. And lastly, just a plug that we will need feedback on this. Obviously, this is very preliminary work, and we are looking for suggestions and contributions as to how to make this useful guidance. So I encourage you to get involved, both if you're a hiker and would like to contribute some citizen science, as well as we'll be holding webinars and in-person meetings coming up. Our goal in the end is to make this usable knowledge. Thank you.